Hello everyone, my name is Loma and I'll be presenting on caddy tracking using Lora and machine learning. Let's begin. Cattle in Southern Africa are the most important possession. In addition to supplying families with the next meal, they are used for different activities like paying lobola, cleansing, thanking the ancestors, as well as more cultural activities. Of lately, cattle theft has been rising in Southern Africa. The Economist reported a case of 218,000 cattle stolen in KwaZulu-Natal in the year 2020, with an estimated increase in 2021. With a sudden increase in cattle theft, there is a need to safeguard and monitor cattle's movement on the farm. There are challenges that are faced in achieving that. Cattle tracking and monitoring devices are expensive, they require internet connections, as well as they need a clear line of sight for proper tracking. They also have a lack of mobility in monitoring devices. These are CCTVs that have that problem. The system presented will have the following: a pendant, a machine learning algorithm to make location predictions, a receiver, and as well as this project will use supervised machine learning, therefore it will compare classifiers under supervised learning. Current tracking devices use GPS. Challenges are faced with this procedure as there is a reliance in connection to GPS satellite. Therefore, in bad weathers and under thick foliages whereby a connection cannot be established, this becomes a huge problem. Some tech introduced Lora Cloud geolocation. This is a technique that relies on internet connection as well as at least 3 gateways, and these are really expensive. This is the breakdown of the technologies. A Wi-Fi module is the cheapest. Lora has a fair range as well as Lora consumes the least power. The machine learning determining technique that will be used is called fingerprinting. This involves using location-specific data to train and identify landmarks. Below is the approach that is used in implementing the fingerprinting algorithms. Received signal strengths as well as name of access points will be used as data to train the algorithms to classify according to the names that are used as the labels of those locations. The classification models that will be used is a decision tree and a support vector machine. A decision tree basically uses conditional statements, whilst a support vector machine formulates a function to separate the data into different classes. The design consists of an ESP8266 node MCU that has a chip which has the machine learning algorithm running on it and making the predictions. These are sent wirelessly using Lora to the mega chip that can then send the information to the monitoring personal computer using serial communication or serial transmission. This is the hardware that was used. The pendant basically consists of a React Lora module which is connected to an ESP8266 node MCU, and a breadboard power supply is supplying 3.3 volts to the whole circuit to power it up. The receiver consists of a React Lora module that is connected to an mega chip, and this as well is powered using a breadboard power supply. The software used is an Arduino IDE, Python, and the libraries that are used is the micro-M-Gen, which is used to create an interface between the chip as well as machine learning. Move on to the implementation. This is in 3 stages: selecting areas, training algorithm, as well as testing. And selecting areas, 6 locations in total were selected at Ashesi University's campus for fingerprinting and testing. These are shown as below. Fingerprinting has 2 stages, which are setting the name of the area as well as collecting the received signal strengths and names of access points on that area. This is a demonstration of how this goes. So the first thing is that you go to the serial monitor. The function that is used listens to a command called scan, and it is followed by the name of the place that you want to scan. In this instance, we're going to be using the potatoes field. This is, remember, directed as Lab 221 in Ashesi University. This is the data that is collected and that is going to be used to train the algorithm. And then we move on to how we create the classifiers. Python is used to create these classifiers, and the Jupyter notebook is the one that is used. Basically, this is how the classifiers were created. We have the decision tree. This is the data, also named as samples, and it basically doesn't take any parameters as compared to the support vector machine. And this is basically the code that will be used that will create the interface between machine learning and the chip in the node MCU. This is the same data, but this case we're using the support vector machine. The difference between the decision tree and the support vector is that the support vector machine has specific parameters. This is the linear kernel. This can be changed. The kernel type can be changed, as the kernel is just a function that you want to use. You can either use a polynomial or you can use a linear, as well as other types. And the gamma that is basically used here is the smallest gamma, and this can be set to auto, and the program will decide on which one best fits. Move to testing and results. The 6 selected and fingerprinted locations in Ashesi University were used to test. The receiver was stationed at Lab 221 while the transmitter was moved from one place to the other. Predictions were then done. This is a demonstration of how this went. So these are the predictions being made in the cassava field, and these predictions are done using an example of a support vector machine. The ID to label function basically uses a switch case to change or convert the IDs that come out of the support vector machine into readable data. that can be used to classify, or that can be used to know where the cow is. This is basically a demonstration of how the AT commands are used to send location predictions from one place to the other. The AT plus send equals to 0 means you're sending on the address 0 and you're receiving on the address 0. Then we move on to accuracy and the testing of accuracy. Accuracy here means the number of predictions or correct predictions over total predictions made. Two tests were conducted using decision tree. These are the results. Test 1 shows a low accuracy with a critical receiving as low as 0.6. Therefore, there was a need for a second test to ensure that we find a way to find high accuracy. And this was done through the changing of the number of samples. And as you can see in the second test, much more acceptable results were achieved. Now we see how this relates, the number of samples and accuracy, and we can draw the conclusion that the number of samples help in training your algorithm to be more accurate. A comparison was then done between the support vector machine and the decision tree. A new location was used to test how both models perform. This was to ensure that this was fair. The decision tree achieved an accuracy of 0.81372, while the support vector machine achieved an accuracy of 0.915699. In this case, the support vector machine was chosen as the final classification model to be used. For accuracy in farms, because this is a sensitive matter, we had to check for robustness in accuracy and consistency in accuracy. And this was done by changing the number of predictions, increasing the number of predictions to see if predictions were done for a longer time, would the accuracy still be high? And these are the results as shown. We can see that there is a consistent way in which the accuracy is achieved, and it is above 80%. And even though in the cassava field there was an undershoot, it still went back up. This means that it can be reliable. And then we'll move on to the conclusion. There were limitations in this project when we were conducting it. There was an ever-changing access point, and this meant that the RSSIs and the SSIDs that we used to train the algorithms were changing, and this was due to mobile hotspots by students on campus, and this made the testing to be done all over again. Inconsistency in the addition of received signal strength was observed from the role model, which made the addition of distance calculations to improving tracking difficult, but this will be further studied in future works. Buildings and topography of the testing area influenced the inconsistency in the Lora models. Therefore, this won't be an issue in a farm as this is segregated from buildings. Addition of a distance calculations with the help of a more reliable and consistent Lora model will be put in future work. Enforcing the robustness of the classification model by using sensor data from farms to create and classify landmarks will be the way going forward. This will improve on the distance of tracking. Then we'll also extend the project to alerting drivers of cows nearby the road to prevent accidents. But this is a sensitive matter as this can also alert thieves, and therefore this needs careful studying if need be implemented. In conclusion, these are the remarks. We have been able to achieve a classification model with an average mean accuracy of 0.92 under the stated limitation. Because of the flat nature and the segregation of farms to buildings and lots of people, the accuracy of this model will even be much higher. Thank you so much for listening.